This video will focus on the different definitions that we have for acids and bases. And then within one of the definitions, we'll actually talk about conjugate base and acid pairs. So you need to be able to determine what those conjugate pairs would be and the relative strength and weakness of the pair. So the first video focused on talking about acids and bases as a concept and giving some general characteristics of them. Now we get into the chemistry. Okay? So there are three different theories behind what an acid and a base is in terms of what the chemical structure is. Okay, and we're going to go through all three theories. Only two of them we really need information on, but I want you to be aware of all three. So really, when you think about an acid and base, what is it? The first definition is Arrhenius's definition, and his definition of an acid is that it's a compound that contains a hydrogen, so that when it ionizes, you get hydrogen in solution. Okay? So examples of those are the ones listed and ones you've seen: hydrochloric acid, sulfuric acid, phosphoric acid. Okay? In each of those cases, when you look at the chemical formulas, they have hydrogen in the formula, which is allowed to come off when it dissociates in water. Three new terms, though, that come up with this first definition is monoprotic, diprotic, and triprotic. What protic level is a measure of how much hydrogen can come off per compound. Hydrochloric acid is monoprotic because if you look at it, there's just one mono hydrogen available to dissociate. Sulfuric acid, on the other hand, is diprotic because you have two hydrogens available to dissociate. So when you put that into solution, you would have two potential hydrogens available from one compound to basically become acid in solution. Triprotic then, phosphoric acid, where you have three hydrogens available to do the dissociating. So what this does in the end, it affects our math in that if we know how much of the compound is put in, you potentially have double or triple as much hydrogen produced. And it's the hydrogen that's measured in relation to being acidic or not. Okay, so an acid is a compound that contains a hydrogen that when put in solution will dissociate, and that's where you get the acid from. Bases in his definition then are just compounds that have hydroxide, so that when they dissociate, you'll increase the hydroxide concentration in your solution. Okay, that's Arrhenius's definition. So acids have hydrogen, bases have hydroxide. There was a problem with Arrhenius's definition, and the only problem comes in, well, predominantly with bases. Okay? Not every base does have a hydroxide. There are times with the compound structure allows you still to make a solution basic without it having OH available to donate into solution. So Brønsted, Lowry took this initial concept of hydrogen donor and OH donor and took it one step further to account for a greater variety of bases. Okay? Acids, instead of just being compounds with hydrogens that can dissociate, are called hydrogen ion donors. Okay? They have hydrogen available to give. So if you think about this, this is basically the same definition, right? Hydrogen available to give, hydrogen available to give. Oftentimes it's called a proton donor instead, because if you look at it, once it dissociates, it's H+. Once hydrogen loses its electron, all it has in a nucleus is a proton. So it's actually simply a proton moving when you dissociate a hydrogen. Bases have a much different definition here. Instead of it being a compound with a hydroxide available to dissociate into, bases are considered hydrogen ion acceptors. They take on the hydrogen. Okay. So if we look at the two chemical reactions below and look at from start to finish, when you put HCl, which is the second reaction, into water, you see that H2O is becoming H3O+. So basically that HCl, that acid, is donating its hydrogen to the water. So you can see where the hydrogen donation is happening. The first example then, if you look at the NH3 into water, your NH3 becomes NH4 and your water becomes OH-. So that NH3, which would be considered your base then, is a hydrogen ion acceptor. It accepted a hydrogen, which makes it a base. And you can see how here Arrhenius's idea of a base increasing the concentration of hydroxide still exists, right? This NH3 compound was able to increase the concentration of OH minus by essentially taking a hydrogen away from water. But NH3 is not a classic Arrhenius base because it has no OH actually in the compound. This change is not made by a dissociation of the NH3. Okay, so that's the main difference between Brønsted, Lowry, and Arrhenius. The huge thing that comes up then with Brønsted, Lowry is this idea that if an acid is a hydrogen donor and a base is a hydrogen acceptor, and remember acid-base reactions are reversible, then basically when you compare both sides of the equation, you can see how there's a relationship between where hydrogen is accepted and donated. And we actually end up having bases be formed as acids donate and acids be formed as bases accept. So in a Brønsted-Lowry definition, every single acid and base you encounter will have a conjugate acid or a conjugate base. What a conjugate means is that as the reaction proceeds, the thing produced by the acid will be a base, because once the acid donates a hydrogen, that new compound has a potential ability to reaccept the hydrogen going in the reverse direction. So if you have an acid, you have a conjugate base for that acid in the product area, and if you have a base, you have a conjugate acid for that base in the product area. So that's all it says. Conjugate acids forms when bases accept protons. Conjugate bases form when acids donate. So that new compound is available to do the reverse. Now, something about the strength of acids and bases. We'll talk all about strength one day coming up here. But the stronger your original acid or base, the weaker the conjugate. So if that acid really, really wants to donate a hydrogen, the conjugate base it makes isn't going to easily reverse to take it back on. It is reversible. They're all reversible. But in terms of magnitude of reversibility, it would have, a smaller or a larger KEQ and not be able to go back the opposite direction. So here's an example for us to look at in relation to this idea of acid-base, conjugate acid-base. So if you look at from start of equation to end of the equation, you're following the hydrogen. Okay, acids are hydrogen donors, bases are hydrogen acceptors. So you look at your compounds and you say, which of my compounds accepted and which of them donated? The donated will be the acid, the accepted will be the base. So HSO4 minus 1 goes from that to just SO4 minus 2. So it donated a hydrogen from start to finish, so that is your acid, your proton donor. H2O, on the other hand, accepted a hydrogen from that sulfuric acid, so that is actually your base in this situation. The acid takes on a hydrogen and is basic based on that definition. Okay. Your conjugate acids and bases then, since HSO4 was your acid, SO4 then is your conjugate base. Every acid makes a conjugate base. So once the acid gives up its hydrogen, the other compound is the conjugate. H2O then, water, taking on a hydrogen to H3O+, that is your conjugate acid. So the base has a conjugate acid. Little language thing here, H3O+ is called the hydronium ion. Okay, OH- is the hydroxide ion, H3O+ is the hydronium ion. Just so you know in case I say it, because I probably will say it in the future. So here's another example. Okay, again, what we're looking for is which of our two compounds gives up a hydrogen and which of them accepts a hydrogen. NH3 in this case accepts a hydrogen to become NH4+, and H2O donates a hydrogen to become OH-. So donating a hydrogen makes it acidic, so water in this case is the acid, and NH3 taking on hydrogen is the base. Okay. Every single acid has a conjugate base, so H2O's conjugate base is OH-, NH3's conjugate acid is NH4+. So every base has a conjugate acid, every acid has a conjugate base. But one thing to notice over these two examples, water served as an acid in one example and a base in another example. Water is actually what we call amphoteric, which means it can do both. It can be an acid or a base depending on the conditions based on the Brønsted-Lowry definition. So it can take on a hydrogen and become hydronium, or it can donate a hydrogen and become hydroxide, serving as an acid or base in every situation. Our last theory of acids and bases is the Lewis theory, and this takes it even one step further beyond what we've been doing. So Lewis acids, rather than being hydrogen acceptors and donors, they're actually ones that accept electron pairs, where bases are substances that donate electron pairs. So you could then look at this and you could have an acid that has no hydrogen, but if it takes on a set of electron pair, you would call it an acid. We're not going to need this definition. It's unnecessary for us in relation to what we're doing, but just know it's out there, and this is the most common definition you'll get to probably using in college. It's so unnecessary for us, it's crazy. Okay, we will just use the Brønsted-Lowry. The minimum number of compounds out there that have acidic properties that don't fit the hydrogen ion donating and accepting thing is really unnecessary for us to focus on. So that's it in terms of the concepts for this video. Go ahead and do the worksheet to see if you understand it, and then do the form, and have a nice night.